Okay, all right. So welcome back. I think the thing is recording. So today we'll continue by talking about fingerprinting of quantum computers. And then I divided the discussion into sort of two parts, more of a background on classical fingerprinting and classical hardware, and then a discussion of few sort of what's been done so far on quantum computers in terms of fingerprinting. So the overall goal is to look at hardware fingerprinting of computing systems first, and then quantum computers in particular. So what is hardware fingerprinting? So if you haven't come across this term before, basically the idea is just like, in a human fingerprint, to find some identifier of the computer hardware that basically can be used to identify it uniquely to sort of differentiate it from other devices. And when we talk about hardware fingerprinting, it usually focuses, I'll explain, on some physical hardware properties of the circuits, of the memories. You might be sort of familiar. Now and then there's sort of some news about browser fingerprinting, where like you fingerprint the software to for example, break privacy of users. So this is kind of the same idea, but this is more about using the hardware properties, not the software properties. Yeah, so the name kind of comes, of course, from fingerprinting humans and having some unique pattern. And the goal of hardware fingerprinting is to find some stable unit identifier that can be used to identify a piece of hardware. So typically, like a server, a phone, maybe a specific GPU board or a specific FPGA board. So the piece of hardware usually means just one computer or one board, and it has many sort of good applications and sort of potential malicious applications. So I think on the positive side, the biggest application of hardware fingerprinting is things like preventing counterfeiting or tracking reuse of electronics. So especially in some sensitive scenarios, especially military, for example, you want to make sure that the equipment that you're buying is new and it's not sort of used equipment that's sort of been used for a while and is being resold. So hardware fingerprinting has been used to kind of detect or identify hardware to make sure that something you're buying is not reused. So like when you manufacture it, you would collect these hardware fingerprints, and then again, when you buy a new device, you would check against, have you seen this fingerprint before or not? Also in counterfeiting. So if somebody makes a fake version of some computing device to ensure that this is really the original one and not a counterfeit. We'll talk about physically unclonable functions, which are sort of related to fingerprints, and these can actually be used to derive cryptographic keys. So oftentimes when you want to sort of, well, actually, anytime you want to do encryption, you need to have a cryptographic key. And then one way of tying the cryptographic key to a specific piece of hardware is to use as a hardware fingerprint, or what we call a PUF, or physically unclonable function, to use those sort of intrinsic hardware properties of the device to derive the cryptographic key, and then use that for encryption. So that's another good application. Another sort of I think it's a good and a bad application, but for example, when you're using a cloud service, you can try to fingerprint the hardware to, for example, figure out how many machines there are in the data center. And on the bad side, which I'll show next, that's bad because you can kind of figure out how many servers of a specific type or how many FPGAs of a specific type there are. But on the good side, sort of the user, if the user is promised, we have 1,000 machines for backup, if you don't see many unique identifiers, then maybe they're not giving you the sort of the so many machines, so the system may be not as reliable as they're claiming. Actually, there's kind of a interesting aside about sort of quality of computation. This doesn't really affect classical computers, but in quantum computing, sort of people are sort of looking at how do you verify something was done on a quantum computer, or that it was done on a specific quantum computer that has good low noise, good quality. So fingerprinting somehow can be related to sort of identifying the quality of the device, although this is mostly, I think, in quantum computing. On the bad side, if you can identify each piece of hardware, especially remotely, then in a cloud data center, you can figure out, let's say, how many servers they have. And That might be sort of some business proprietary information. When you rent like a virtual machine from Amazon, you don't actually know how many servers Amazon has. But if you find a way to identify all the hardware, that could be problematic. Actually, we had some research a while back on fingerprinting FPGAs and figuring out how many FPGAs there are in the data center. It's easier than CPUs because in FPGAs you have access to the hardware, but kind of maybe more on a nefarious approach of figuring out how many things there are, even if the cloud provider is trying to hide it. And of course, if this is sort of not for the infrastructure, but for the users, then, you could de-anonymize the users if you can track their hardware. So I think for hardware fingerprinting, it's really, these main ideas that are kind of the purpose of having the hardware fingerprints. And I mentioned that there are these two terms. I don't know if anybody has heard about puffs before. That's very maybe okay. It's very very hardware security specific, but puffs are called physically unclonable functions. And then the idea, so it's similar to the fingerprint in that the output of the puff is somehow related to the physical hardware properties of the device. The difference between the fingerprint and the puff, the simplest way maybe to describe it is that the fingerprint is basically something that you fully just observe. You collect the fingerprint, like, you get the fingerprint. But for puffs, there's actually an input. So you have some input, and then the output of the puff depends both on the input, which is usually digital, and then the physical properties of the hardware. So you have this challenge response pair. So it's sort of you send a challenge, you get a response, and then that response depends on the challenge and on the hardware. So whereas for a fingerprint, I have one fingerprint, and once you collect my fingerprint, you know my fingerprint. But for puffs, since you can give different inputs, it's sort of like having a set of many fingerprints for that one device. And unless you know the device and the input, you cannot generate the correct output. So it gives you more flexibility, and it's usually used for cryptographic keys. That's one of the main applications for puffs. So for fingerprinting, it's a unique hardware identifier. Usually I'll show some examples due to manufacturing differences. So, if, let's say every phone of certain type has the same component. So the way you can identify it is not by the components they have, but by the manufacturing changes within the components. And then these changes can be either observed by directly reading out some state, like I'll show some SRAM and DRAM puffs where you directly read out the state. But you could also maybe use power, EM, or sort of some measurements of the device to differentiate it. And in a way, fingerprint is more like a side channel. You just collect some information from the hardware. And the puff, again, it's similar. The output depends on the manufacturing differences, but you have this idea of the challenge response pair. So if you remember, one thing about puffs is that it's tied to hardware, and then these are they call them CRP, challenge response pairs. So you basically probe the hardware with some input, and then the output depends both on the input and the hardware properties. And I'll show an example of an arbiter puff to give you an idea. Question.
Type of thing where I give one challenge and based off the one response, I would assume that I know it, or would it be I give multiple and then the chances of it having multiple the same?
A good question. So usually you use one challenge and one response, but then the reason you can have many inputs is that once you use a challenge, somebody might see it. So once you use a challenge, then whoever's observing the system might, okay, no, this challenge gives you this response. So for puffs, typically you want to have many challenges, so you could probe it many times, and from each response you get the result, even if somebody, so it's a sort of a new result, so that somebody couldn't reuse your prior challenge.
Yeah, things like the time on wherever that can vary over time, or with environment or age or how does that like?
Very, very good. Yeah. So one, I'll mention a bit. So one challenge with puffs is that they have to be stable over time, and then basically, yeah, as the voltage changes or as the temperature changes, the output has to be sort of similar. So when you're designing a puff, or when you're trying to sort of fingerprint the hardware, you have to find something that's very stable. And if it's not stable, then it's not useful for a puff. And then also, if if many devices give you similar result, then that's also not good because you want to identify it. So you have to have, so usually we talk about stability and uniqueness as the two properties. But that's exactly right. If things change too much over time, then this is not very useful. Very, very, very good point. And and then one thing actually for fingerprinting, it's more like you're just observing the properties of the device. For POFs, since they're quite often used for cryptographic key storage or to get cryptographic keys, they might actually be added on purpose to the hardware. So you might actually put in a dedicated circuit or use a dedicated piece of memory as a POF. So it's sort of something that you can put in during manufacturing, for example. Um, oh, okay, perfect. Like actually what you were just asking. So some characteristics of the POPs is the stability. So it has to be basically over time or over temperature range or over voltage range, the output has to be the same. And then usually the output of a POF is a set of digital signals. So then you can compute what's called an intra-Hamming distance. Basically, you compute how different the digital outputs are from each other. And then, for it to be stable, they have to be so you have to have a low intra-Hamming distance. So it's similar. The other property, the uniqueness that I was mentioning, basically each path has to give you some unique values, so that you can identify if many devices give you similar values is kind of kind of useless. And then some other properties for paths is unclonability. So this actually means that you shouldn't be able to make multiple devices that have the same challenge response pairs or have the same characteristics. So that's actually, I guess, why they're called physically unclonable functions, because if you're leveraging the physical manufacturing changes, these are hard to replicate, and then that means you cannot really clone it. There are many attacks on puffs, like trying to model them, so that's a problem. But ideally, they're unclonable, and then also for some applications, it would be nice to have tamper evidence. If somebody messes with your device, that actually changes the properties of the puff, and then now you can detect that somebody has messed with it. So there are many challenges. The devices they age or they get worn out. Environment changes, and also if it's too easy to model or simulate the puff, it's kind of not useful. But there are many types of puffs. And before we go to the next section on the quantum computer puffs, I just thought to kind of review what's been done in the classical hardware. And again, this is sort of the picture. In general, you have a piece of hardware, and then the goal is to extract some unique characteristic that gives you this fingerprint. And they're almost always based on manufacturing variations. Yeah, we're talking about identifying the number of machines, or actually, maybe I mentioned a little bit. If you can actually identify the machine, then okay, you identify the machine, but also maybe another application would be to identify, for example, how often a certain machine is assigned to you in a cloud-based environment. So these are kind of some goals, and there are a few types of puffs. I'll just talk about SRAM puffs, DRAM puffs, and circuit-based puffs. And I wanted to give credit to this. I borrowed this figure from the semi-engineering website, but it was very nice Northwestern colors, so I thought I can use it. But so SRAM puffs. So how many of you remember how an SRAM cell is designed? Okay, perfect. Right. So in the SRAM cell, basically use a set of transistors to keep it like a feedback loop to store the values, and then where the manufacturing variations come in is when you fabricate each SRAM cells. The transistor sizes change a little bit, the wire sizes change a little bit. So actually each SRAM cell within like an SRAM memory on your processor, on your system, is slightly different. And then what people sort of observed is that when you turn on the device, the initial state of the SRAM before it's actually erased and initialized to all zero is kind of sort of random, and it actually depends on the, if one transistor in an inverter is bigger than some other transistor in the other inverter, that might push the value of certain cells to more often initialize in one, and then maybe some other cells more often initialize in zero. So in SRAM paths, the realization was that when you turn on the SRAM, due to the manufacturing variation, the initial values of the SRAM cells are different. And so if you're able to kind of read out the memory as soon as it initializes, you get this random looking pattern, but it depends on the hardware, and each piece of hardware will have a different pattern. And then since SRAM cells are just binary values, then you can just read out the initial value of the SRAM, and then get your 256 or 512 bits, however many you need for example, devise like a cryptographic key. Doesn't make sense, hopefully. So this actually it's not in the slides, but this we would kind of call it like a weak path, because there's really so we talked about the challenge response pair side. So here, since you're just reading out the initial value of the SRAM cells, there's not direct like an input. So when you have an SRAM path, the input might actually be the set of addresses. So you have like a big SRAM module, you read first 256 addresses, that's the first challenge. Read second 256 bits, sorry, that's the second challenge. So like the address of the memory region might be the input, and then the output is the unique pattern in that region. And it's weak because you just have sort of the number of challenge response pairs is sort of linear in the size of the chip. So it's kind of limited amount of challenge response pairs. Oh, okay. Actually, just a small aside. So actually, I mentioned that puffs are sometimes added. So there used to be a company called Intrinsic ID, which I think not very 2 years ago, not long ago, was actually acquired by Synopsys. So if you're ever fabricating a piece of hardware and you want to have a unique hardware fingerprint, you can actually add a intrinsic ID SRAM puff into your ASIC chip. And when it's manufactured, it contains a little dedicated region of SRAM that's purely used for these fingerprinting. And one reason why you might have a dedicated SRAM puff instead of just reusing the SRAM memory is that, again, this requires the startup value. So you have to sort of reset the SRAM and read up the startup values, which is not easy to do when the system is running. Okay, just very quickly so we can get to the quantum puffs. There are also DRAM puffs based on dynamic random access memory. So do you guys remember how the DRAM cells are made? What's in a DRAM cell? Right, so each cell is one capacitor, and usually one capacitor and one transistor. And then, as I think when we talked about Rowhammer, we mentioned that these DRAM cells can decay. So the idea for the DRAM paths is not like SRAM paths where it's based on the startup values. It's based actually on the decay. So this figure kind of tries to show that that basically if you initialize the two different DRAM modules, let's say you write all once to different DRAM modules and let them wait for some time for the capacitors to decay, certain bits will flip. And then basically, over time, different bits flip, and then which bits flip depend on the manufacturing variations, like which capacitors were bigger or smaller, or which transistors were maybe more leaky. So so you can initialize DRAM, turn off the refresh rate, and you get this fingerprint, and that's been used for example, fingerprinting FPGAs or cloud servers. And then here maybe one challenge is that you need to disable the refresh rate. And then just last example of the puff. So this is it's an arbiter puff. It's type of a circuit puff, but in these puffs, instead of looking at the contents of the memory, you actually look at the delay of the propagation delay through the circuit. So it's maybe a little messy picture, but basically the idea is that you have some input signal, and then you have like this number of stages of multiplexer. So basically, hopefully you remember, in a multiplexer, you give it a control signal, and it chooses between one of the two inputs to send to the output. So if you so here actually the input or the challenge to the path is the configuration of each of the multiplexers, and then when you send the signal based on whether it's 1 or a 0, one signal might go one way, and then the other signal is going to go the other way. And then at the end, basically, the output is whichever signal arrives first. So you're sort of looking at the propagation delay changes through these multiplexers. And with n bits, you have sort of 2 to the n different combinations. So you can have 2 to the n different challenges. And then for each input, for each configuration of the muxes, you send a signal through them, and then you decide which signal arrives first. And that's so from an arbiter path, you get 1 bit, and then you can just replicate this many times. So this sort of gives you an alternative idea that instead of using things like manufacturing variations in the capacitor sizes, you use the differences in the propagation delay due to the wires of the transistors.
Wouldn't it be less stable though, because sometimes like heat up your board and now your propagation delay.
Right. So those are many. I mean, it's actually similar for DRAM, right? If you heat up the DRAM, it's going to decay much faster. So if you can sort of for DRAM paths, one challenge is that you're supposed to wait for some small amount of time, but then if you heat it up, that changes. And then so I think you can have a career out of designing puffs. So there are many ways, but the dealing with the environment change is a big issue. And then nowadays also people use machine learning to model these. So you can sort of if you can model the propagation delay, then even there are sort of 2 to the n different combinations. You can they're actually pretty good at guessing the outputs of the puffs. So this the environment and modeling of the puffs is a problem.
So does the machine learning approach work with environmental changes?
I don't know the latest literature, but it's pretty good. That the approaches are pretty good. But that's something to look into how well it handles the environment changes. And then and maybe unlike the DRAM paths, for example, which are already in the DRAM is on the classical system, you have for this you really have to add a dedicated circuit. Okay, so I don't any questions about the classical paths? I think pretty easy. I think that the takeaway message is that sort of we're looking at different hardware manufacturing variations to decide what's to find some unique properties of the hardware, and then based on that you get a fingerprint, which might be based on the response of the delays or just reading out the DRAM paths. Okay, so now don't have maybe half an hour left. So I want to kind of jump in and discuss the fingerprinting of quantum computing systems and kind of how people have approached it so far. So this is our favorite picture of the quantum computing system. And just as a quick review, so far in the prior week we talked about the side channels on the controllers. So I think that part we covered. So today we'll talk about fingerprinting, and within the fingerprinting, basically you have what you might want to fingerprint, right? So one focus could be fingerprinting the cloud infrastructure. Let's say guessing how many quantum computers there are, how often they're being scheduled. Fingerprinting the controller itself, since the controller is directly tied to the QPU. Then if you can fingerprint the controller, you can basically fingerprint the QPU, or fingerprint the QPU, or fingerprint some hardware that's quite often now people are using GPUs to optimize the circuit parameters. So, if you assume the quantum computer is in the same data center as the GPU or as the high performance computing infrastructure, if you fingerprint that, then effectively you kind of fingerprinting the location of the quantum computer. So there are four options, and I think today we'll focus on some examples of fingerprinting of the QPUs. This is, I think, the target of most recent work and quite a few research papers. Fingerprinting of the controller infrastructure. I think it's an interesting idea, but the users usually don't have access to the controller. For fingerprinting the QPU, you can submit a circuit, execute it on the QPU, and get the results. For controllers, you don't really have access to them, so maybe interesting, but maybe not practical. So we'll not cover that. Fingerprinting the GPUs or the high performance computing infrastructure. I think that's really interesting, but that's maybe already covered by like these DRAM puffs that have been proposed in the past. So this is really just classical. And then last but not least, fingerprinting cloud infrastructure. So this actually we'll not talk about either, but it's quite interesting if you can, you can deduce some information from the way the quantum computers are assigned or reassigned to users or scheduled. Right now, basically, so far all the quantum computing companies really tell you the name of the machine or the ID of the machine. So fingerprinting the cloud infrastructure might be less important, but in the future this might be kind of a gain in importance and popularity. So next rest of the meeting, we'll really focus about the QPUs. In these slides, sort of kind of want to summarize some last few years different works that people have looked at fingerprinting QPUs from different perspectives, and this is actually one of the first works. So when you develop the fingerprint, like I said, the question about the environment or things changing over time, you really have to find out or figure out what are some good properties to use as a fingerprint. So actually, one of these first works looked at finding the good properties for fingerprinting quantum computers, but at the same time finding out what's not good, right? So if you want to kind of eliminate these things that vary over time, or actually in this case things that don't are not useful as fingerprints. So here just some graphs to show, but the takeaway message is that in quantum computing we have things like the T1 and T2 times for relaxation and dephasing. So this is basically how fast the qubits are can lose their state. So everybody kind of wants quantum computers with longer T1 and T2 times have better quality, but they are kind of a physical property of the qubits. But for example, if you look at these graphs, they just basically try to show that for different QPUs or different qubits within different QPUs, these properties are very similar, so that you wouldn't get like a very unique fingerprint. Also things like readout error, very similar for many machines, so you couldn't really get a unique fingerprint. For CX or 2-qubit gate operations, again, the error, the gate error, or how noisy the gates are is pretty similar. So these were sort of all, let's say, manufacturing variations or manufacturing imperfections, but they don't really give you enough sort of uniqueness to be used as a fingerprint. Yeah, so maybe some things to ignore, at least for now. But actually, one property that turned out pretty useful for fingerprinting is just looking at the qubit frequency. So as we discussed before, right, at least in superconducting quantum computers, different qubits have different frequencies that they operate on. And then so it turns out this can be actually a one use or one way of having a fingerprint, that because the qubit frequencies are on purpose designed to be different to avoid interference, they're quite different and can be a basis for a fingerprint. So so one of the first quantum computer fingerprints, but also pretty easy to devise, was based on the frequency. So here, these are just a picture of the qubit frequencies for different IBM machines, and this you can see that this is actually getting a little bit old because this was a 5-qubit machine from a few years ago. So it's but it kind of demonstrates a principle that, for Bogota, Santiago, or Manila, for these different IBM machines, each qubit, qubit 0 to 4, had different frequencies. So these seem to be sort of unique to each qubit, even across machines. And quite interestingly, going back to that question about environment, they're pretty stable. So a calibration cycle, I believe at that time, was about either 12 hours or 24 hours. So you can see that over tens of days or longer, the frequencies for a specific machine are pretty stable. So you could use that as a fingerprint. I'll show an interesting problem a little bit later, but you have these qubit frequencies, which are at manufacturing time. They're slightly different, but they're not fully controlled actually by the manufacturing either. So they're different on purpose, but they still vary a little bit. So it's hard to get 2 qubits with exactly the same frequencies, even if you wanted to. So, but here, just kind of showing the heat map that, for qubit 0 on Bogota, has the same, of course, the same frequency to itself, but it's much different from the other qubits. So the darker the color, the bigger the difference in frequencies. You can see that they're pretty, maybe with like 1 or 2 exceptions, the qubits are pretty unique in frequencies. And so based on this, there was a simple but I guess very workable a fingerprint, which basically is just a vector that identifies the set of frequencies. So the set of frequencies of the qubits, which you either are provided by the quantum computer manufacturer or measure yourself, is the fingerprint. And then so once you have a fingerprint, you also need some way to compute similarity of that fingerprint. So here, instead of using these Hamming distances that I mentioned before, basically the fingerprint was computed based on the number of frequencies that are different, divided by the total number of qubits in the machine. And since the frequencies can vary a little bit, the comparison is actually not, there's some small delta that's concerned. So if 2 frequencies are within some small range, then you assume that they're same. So this takes care of a little bit of the noise and the variation, and then it's divided by number of qubits. So it's pretty easy, and it actually works very well. So this shows kind of the across many calibration cycles, you can see that the fingerprint is almost identical, and then but across different machines, you get quite different. So you can use that to identify the QPU. So instead of using like a startup value or the decay for like in the classical machine, this just uses the frequencies which of the individual qubits. Any questions about this fingerprint? So yeah, so basically, once somebody is able to run a circuit on a quantum computer to measure the frequencies, or maybe they're even given by the quantum computer provider, then they directly know which machine it works. And this is really cool. There's actually a small problem though that's kind of also interesting. So this is some data from a while back from our collaborators, but what was found out is that basically, although under normal operation, the qubit frequencies are pretty stable, when you or if there is some really big physical change to the system, for example, the quantum computer is turned off and the qubits are warmed up, and then again you cool it down. Actually, they observed a significant change in the frequency. So this is kind of just a graph showing the frequency of the different qubits, and then you can see that during certain periods where where the machine was warmed up or was offline, actually the frequency changed quite a bit. So it's kind of a interesting observation. I don't think anything specific has been kind of published on this, but it kind of shows that there could be changes in the qubit frequency. So on one hand, it breaks the fingerprint that I showed before, but on the other hand, this actually can be used to identify if there was a change. If somebody tried to open up the quantum computer and then they put it back together and turn it back on, you'll see the changes in the qubit frequency. So that could be if you use a machine, you collect a fingerprint, and then a few days later you have a radically different fingerprint, then you can identify that something was changed in the infrastructure. So kind of as things go, on one hand, its frequencies are pretty good, pretty stable, unless you open the machine. But then if you open the machine, that might actually lead to a change. Any questions about these? This is sort of purely based on the fingerprints. I'm sorry, on the frequencies. Okay, all right. So kind of jumping to kind of different type of fingerprints. So these frequencies are kind of properties of individual qubits. What if we look at some sort of interaction or noise or crosstalk among the qubits? And then another type of a fingerprint that was proposed is basically looking at how different qubits react to noise, and then identifying them that way. So it's based on this idea of idle tomography, which kind of in a simplified term, effectively you have different qubits, and then you keep certain qubits idle, so they're just not doing anything, and then you perform some gate operations on another set of qubits, and then you observe how the gate operations affect the idling qubit. So basically, I guess that's why it's idle tomography. You're keeping the target qubits idle, and then you're trying to observe how they're affected by the errors. And because of the topology of the quantum computer, because of the manufacturing differences, different qubits within the machine would sort of react slightly differently to this noise, and then that could be your fingerprint. So when you're having these fingerprints, maybe I didn't describe it so clearly for the other parts, you have to sort of enroll or figure out what are the possible fingerprints, and then you actually do the matching. So in this case, in the enrollment phase, sort of the attacker, let's say, would get access to the whole computer. And again, this is getting a little old, but this is a topology of what used to be a 7-qubit IBM machine. It's kind of like this I-shaped topology, and then basically before you can kind of create the fingerprint, you have to learn how the different qubits react to noise. So in the enrollment phase, you would the attacker or whoever wants to fingerprint the machine would let's say rent the whole machine and then try to analyze how the qubits are responding to noise. So so this is kind of one example where, for example, if you have access to the whole machine, you take some circuit, let's have some simple 3-qubit circuit, and then you sort of map it to different physical qubits, and then you try to observe this noise. So like if these three qubits get mapped to these three physical qubits, then the qubit 2 would experience a certain amount of noise. If you take the same circuit with same three qubits, but now this qubit 2 gets mapped to this physical qubit, from the circuit perspective, this is it's the same qubit, but it's now using a different physical qubit, which will have experience different noise and error. So you basically map each circuit to different locations within the machine and see how they're responding to this noise. And then, yeah, just you can have on this type of machine, you can have different layouts, and then there are different machines maybe less interesting. But now the key part about the using the fingerprint is once you have collected all this information, you might you could request a circuit to execute on a quantum computer, and then you get allocated some subset of the qubits, which you don't know that's what you're trying to fingerprint, and then basically by looking at the error information from the tomography, you try to figure out try to exactly figure out which part of the quantum computer you're using, or which machine. And you can do some classification, but maybe in the interest of time, just one example to show that as you have these bigger circuits. So this wasn't so clear. So these different P, L, and T, they're just different test circuits. You can think of like the attacker is using more qubits to do the fingerprint. So the more qubits they use to do the fingerprint, the accuracy gets better, or the more times the more experimental batches they run, they get more information. So this just kind of probably predictably shows that as you use more qubits to fingerprint the machine, your accuracy would get better, and in some case, in all of these cases, close to almost 100%. So by looking at the noise in the qubits, you could use that for fingerprinting. So now this is different approach from using the frequencies. Any questions about this part? Okay, all right, cool. So so last section, jumping kind of more from fingerprints to puffs for so again with the fingerprints, you just have sort of you observe the operation of the system. With the puff, maybe you have some option to give it this challenge inputs to get different responses. And I didn't show our favorite picture again, but you could have puffs that target either the QPU, the controller, the HPC, or the GPU, or the kind of high performance infrastructure, or the cloud infrastructure as a whole. And I think that the most interesting and what people have been looking at are the puffs in QPUs, which I'll talk about. It's basically, again, using the qubits and their properties. I guess puffs in the controller would be kind of interesting to fingerprint the controller, but again, the access is very limited, and not clear how this would be different from just a regular SRAM or DRAM puff. So maybe puffs in the controllers are less interesting. Similar for GPUs and other things. Again, they're already just classical components, so puffs in those are less interesting. And I grayed out the cloud infrastructure. Both fingerprints maybe less, but puffs are really tied to a specific device. So puff at like the infrastructure level, I'm not sure if it makes sense. I mean, you can have puffs of the individual machines, and that you can use that for building information about the infrastructure. So maybe this last one just not sure it makes sense. So I graded out. But the puffs and the QPUs are the most interesting. So okay, so last few slides, Diff just kind of show you some ideas of what's been proposed for puffs and how they work. So I think this was one of the early puffs, quantum puff, kind of a nice name. But basically, the idea in these quantum puffs was that again, you need some input, and then you need to try to use some quantum properties. So in this case, for example, there's a gate-based puff or a decoherence puff. So the idea is that you initialize the qubits into different states, and then, for example, you apply Hadamard gate to each each of those qubits, and then you perform a measurement. So in this type of circuit, the output, of course, depends on the initial state of the qubits, but it also depends on the noise, for example, within the gate. So as different gates, or sorry, as the gate, as the same gate executes on different qubits or on different machines, they all have a little bit different noise. And then so the idea is to try to capture that from this. So this is less about the not like the fingerprint based on sort of the idle tomography. This is more on capturing the noise of the gates and using that for to read out the path. And then just as a classical path, once you have a measurement, you have a classical output, and then that can be your response from the path. And then another path based on this decoherence, or basically you initialize different qubits to different initial states, and then basically you just let them idle. And then although we saw before that maybe the T1 and T2 times are not so good for fingerprinting, at least in this work, they claim that this could be a possible one used for a POP. So again, if you have some variations in the T1 and T2 times for the different qubits, you might be able to use this to identify the different machines. And yeah, and then sort of just kind of showing the probability of the output. So you can see that you have for different rotation angles, you have so here actually I should clarify that. So the input here was setting the different qubits by rotating them into different state, and you can see that as you change the rotation angle, you get different output probabilities, which is this idea that for different challenges you can get different responses. Yeah, and then we already talked about the Hamming distance, the intra and inter-Hamming distance. So here again, once you do the measurement, you just get classical bits, so you can compare the distances, and then inter-Hamming distance is from among different items, so from different paths, and then ideally it's a large value. So as you compare different paths, there should be a large value. Intra, within the same path over time or over different measurements, you should get the same result. So this is the specific graphs are not so interesting. I borrowed from their paper, but the idea is that, again, for the inter between different machines, you can see that you have a bit over 50%, quite a bigger Hamming distance, and then within the same machine, it's trying to get to close to zero. So it's pretty maybe not ideal, but pretty stable. So it's kind of so now you're using the intra distances and intra distances to compare the POPs. And then this I think that actually this table I found it it's actually a very interesting matrix comparing different types of POPs, and then I think this is actually a very, very interesting way of thinking about POPs in terms of what is the device, and then what are the challenge response pairs. So before at the beginning of the lecture, we talked about classical POPs. So the device is a classical SRAM, DRAM, or a circuit, and the input is some classical information. So the beginning of the lecture was sort of these classical POPs where device and the CRPs are classical, but you could have also other things, like you could have a quantum device and a classical input, which was what we just talked about. We had a quantum circuit that has some classical input, which is the rotation angles. So the input is the rotation angles. The output is the measurements, which are classical bits, but the device is a quantum device or a quantum circuit. And then there are two other ones. There's a quantum input for a quantum device. So this has been proposed, but hasn't really executed because you need quantum networking or quantum memory to provide the input. So instead of inputs being classical, they could be quantum states coming from somewhere. So that's one proposal. And then very very interesting. We haven't looked at it much, but this idea of providing quantum input to a classical device. I believe the one example from this work is like basically if you send like a single photon to a regular camera detector, so some sort of basically the device is classical, but you're using quantum inputs and how it responds. So kind of interesting categorization. In this work, they next two or three slides talk more about the classical input and classical output by a quantum device. So similar to what we saw just earlier, you have some different challenge and response pairs that you collect to build the information about the device, and then when you actually run, you send one of the challenges and you collect the response, and then in this work, again, the input is classical, but for example, instead of having one layer of these rotation gates, they had a few layers of different gates, and this was their proposal. But quite I think very very important, and actually the end conclusion of the work was that a lot of the paths with the classical input, classical output by the quantum device might not be actually so good because you can actually model the behavior of the device quite well. So if you can model the path, then it then kind of defeats the purpose because you can just generate the output. So they did talk about the CR path, which is similar to the quantum path, where you have the classical input that controls the orientation of the qubits. But they also show that you can model this quite easily. And then so yeah, maybe actually a nice figure from their work kind of summarizes the idea that in a path you should be able to send a challenge, and only the right person should be with the right hardware should be able to respond. But if you can model the behavior of the path, how the qubit noise, for example, affects the result, then somebody could take the input and then respond with a correct looking output, but defeating the purpose of the path. So again, so some benefits, but I think the takeaway message, I think this table is really nice. You have the CR path or the quantum path, where you have a classical input to a quantum device. Of course, you have purely classical paths. You have this quantum input to a classical device, and then this sort of quantum path where the input is quantum. So that I think most people have so far focused on this classical paths, but I think in the future, as we get quantum random access memory, quantum networking, as things get integrated, then you're able to send quantum states directly to the quantum computer, and then so you could actually you could use those quantum CRPs to challenge the device to kind of give you the right result. So to maybe close with our favorite picture, you can have POPs or you can have fingerprinting in many parts of the quantum computer. A lot of work has looked at the QPUs themselves, like using the crosstalk or using the gate noise, things that we discussed for QPUs. Fingerprinting, the cloud infrastructure, I think kind of remains an open challenge, kind of can be interesting, but the paths there are unclear. And then for the controller and then for the HPC, then fingerprinting might be interesting. The paths are maybe a little bit less, but this kind of gives you a kind of again the summary. So I think most interest continues to be on how do you kind of fingerprint QPUs, and especially now if you go to IBM or another company, they tell you the name of the machine and then tell you everything. So maybe fingerprinting is not so I don't know like how to say it, critical, but in the future when you have tens or hundreds of quantum computers and you no longer get any, IBM just tells you you got a quantum computer, but they don't tell you which machine, then the value of the fingerprinting will keep increasing. So I think in the short term, yeah, maybe the value of fingerprinting is a bit low because you know the machines anyway, but in the future, the value of the fingerprinting will get much more significant. Um, Okay, so right, so to finish up, hopefully you got some introduction to fingerprinting and puffs. Try to remember what a puff is, if you remember one thing, and discussed most of the quantum related puffs that are out there. Basically, again, measuring the physical properties, which most often so far are related to noise and kind of imperfections, the quantum computers. And and we'll continue talking about all the other topics next time. So yeah, let me end here. And